Hi, I'm going to present our research SoundMorphTPU exploring gesture mapping in the formable interface for music interaction. Our research is based on background into materiality and tangible embodiment and deformable interfaces in DMIs. And the fabric-based interactive surface is one category that we are focusing on because it typically involves multi-gestural interaction. And we are interested in gesture mapping such as the I/O relationship, and we identified the gap by literatures is that there's a lack of exploring the I/O relationship in the formable interface. And our research also took inspiration from methods for material exploration, such as user elicitation studies and material probe. Then we raised our research question. Then we begin our exploratory study. We have 5 material samples in 3 sizes and invited 8 participants as amateur instrument player. And the test is they interact with the samples, imagine using gesture to generate sounds from it. And the process was video recorded, and participants also report the imagined sound during the test. And here are some results. Let's have a look. Finally, we got some results about the applied gesture for each fabric samples with the imagined sound arose from participants. Some common gestures were shared among different material samples such as jack, and we noticed that single hand gesture appear more in smaller and medium-sized shapes. The exploratory study demonstrated that different fabric materials may invoke different types of gesture to interact, and the feeling towards the sound produced by fabric is also unique to the materiality. This inspired us to explore further the relationship between the applied gestures and the type of sound control in our main study. And we chose TPU fabric, thermoplastic polyurethane, as the proof of concept material, as it has been shown effective in being manufactured into a sensing unit. Here are some gestures based on interacting with TPU, where we are finally targeted at on our probe. After choosing TPU as the material, we began to prototype the main material probe of the study, which is named SoundMorphTPU later. The main goal was to develop it as a sensing unit, which allowed the target gesture we chose. While developing this, we aimed to avoid compromising the original materiality of the fabric. Considering the sensing technology, applying embroidered conductive is not appropriate, and attaching another sensor unit will harm the transparency as well as influence the materiality intensively. We chose conductive ink printing as the manufacturing approach. The conductive ink we use is based on single crystal silver nanoparticles. We printed the conductive pattern with a programmable dispenser with a piezoelectronic nozzle. We programmed the pattern using the dispenser software. We stabilized the TPU fabric with an hoop and tape during the process. We repeated the printing process twice to ensure the conductivity and then cured the printed ink in a chamber at 85 degrees Celsius for 30 minutes. The printed trials take several times, and we iterated the prototype methods and tried it with some sound triggering techniques. Sensing pattern and circuit scheme of SoundMorphTPU consists of units with 2 circles placed at the beginning and end of a line. Each have a diameter of 10 mm. We tested the prototype in Arduino IDE. The deformation of each sensing pattern results in continuous changes in the input pin's analog values. When the printed pattern is deformed, its resistance and the analog value output in Arduino IDE changes. Then we tested each pattern using visualizer. The deformation of each unit is distinguishable. After that, we linked the signal input to Vakinator, an open source software for using machine learning to train different gestures. The link with MaxMSP interface to experiment it to trigger music samples. For the sound design, we select 6 effectors including pitch shifting, reverb, flanger, chorus, and EQ filter, and delay. We programmed them in MaxMSP to link with Vakinator. And also, we have a video describing the sound triggering mechanism. The main study was conducted in a quiet environment, and we provide headsets to participants for listening to the samples. SoundMorphTPU was connected to a laptop. We also placed a traditional music controller launchpad to invoke discussion. The study design is a within subject design. We have 4 independent variables as gesture and 6 dependent variables as sound effects. We invite 12 participants who are HCR researchers or students to make it not limited to DMI designers. This is the quantitative findings of the study. First, let's have a look at sliding. When trying to control sound effect with sliding, some participants make the analogy with real-life scenarios or nature, such as interacting with water. 5 participants emphasized sliding as a directional gesture. Tapping is very obvious in instant changes. In addition, 3 participants mentioned that the tapping gesture gave them a strong sense of how the sound changed through the movement of their fingers. 2 participants mentioned the gesture as rush and messing up, and chose the effector based on this. Poking on the fabric-like surface also shows a connection with other scenarios. Analogies with switch button were most common, and 3 participants reported the feeling of sound effect corresponding to this gesture should be instant. One very interesting finding is that 3 participants mentioned they think of poking people, that people produce funny sounds, which is the effect of pitch shifting and flanger. For patting, the most obvious findings was the analogy between interacting with the fabric surface and other things. This includes patting on a ball and making some bouncing sound, covering the sound with something to filter out some noise. We also discovered the perceived benefits of using the deformable interface for sound control, like portable, flexible, and it can be considered as another layer of an existing instrument. It also invokes intuitiveness and playability. For beginners, it's regarded as easy to use, and it can trigger exploration. It also provides richer sensory experience. For example, it triggers the desire to pay close attention to the sound. And it has the potential to control richer sound parameters, discussion, and future insights. During the study, we found the 3 main concepts related to gesture sound mapping in deformable material. First is sound association based on analogy and sound deformation. And also, the mapping can be thinking of instant or continuous. And also, we discovered the fabric-like deformable interface for multi-gesture music control and its potential. The future direction can be further focus on the sensing technology to enable the detection of direction or intensity of the gestures. And also, the sound mapping in other deformable material can be explored. Also, it will be interesting to combine different multiple materials in the design of digital music instruments. And that's all. Thank you.